Okay, YouTube, in this last video of an application of determinants of matrices here, we're going to look at another extension of our formula that we use to find the area of a triangle given the three vertices. And so recalling here that our area of a triangle, if we have three vertices here, let me switch over my pen tool here. The area of a triangle having three vertices here, remember, was plus or minus 1/2 times this determinant here where we have ones down our last column here. But basically, we drop in our 3 points here, x1, y1, x2, y2, and x3, y3. And so this holds true. Basically, in this video, what we want to do is find the equation of a line given 2 points. And so, this might be something that we have here. Certainly, we could find the equation of any line given 2 points by using non-deterministic methods, I guess, non-determinate, methods, I guess. We wouldn't have to use a determinant. But if we wanted to use a determinant, what we're going to kind of explore here is this. In this example here, let's go ahead and label this. We say this is x1 and this is y1. And this would be our x2 and our y2. And so we could say, generally speaking, we have 2 points on this line. We want to find the equation of the line that passes through it. So I'm going to go ahead and pass this line through it. And one thing that I want to observe is this. We don't need. But if we were to explore this as, let's consider that this point right here, I'm going to label this xy. This is an arbitrary point on the line. An arbitrary point on the line. That means that it's not any specific point, but it's definitely a point on this line. What I want to explore is this. Maybe, just maybe, if we knew two numerical values here, and so that would mean we have number, and then ones over here, and we left this last one here, this last ordered pair, is just an x and just a y, and it represents every other point on this line no matter what, then we could say if the area of the triangle having these 3 points as vertices equals 0 when they're collinear, then what we'll do is we'll take this formula here for area and we will purposefully set it equal to 0. And instead of putting 3 ordered pairs that are known, we're going to take out, say, this first one here, and we're going to replace it with just an arbitrary x and an arbitrary y. Excuse me. So one thing I want to comment on here before we kind of go over here and take a look at this formula, but is this. We're just basically going to find this determinant over here on the left, but one thing is for sure. If all of this equals 0, then if I were to say take both sides times 2 over 1, multiply by the reciprocal here, 2 over 1 times 0 is just 0. So what we're really doing in this video here is we're saying the area is 0 because we want these to be collinear. We're just leaving 1 point arbitrary is all we're doing. And we don't have to pay attention to the plus or minus a half because what we're doing is making sure that it is equal to 0 in the first place. So this formula you see here, it says the equations of the line passing through the distinct points x1, y1, x2, y2. So you got your 2 points here. By the way, I'll mention that that these are here. Just to kind of visually support this, we say here's our first ordered pair, here's our second ordered pair. And I don't really want to write that there, but I want you to see that. This right here, this x and this y, that's our arbitrary point. And so maybe that's something that we want to write right here. These right here represent any point on the line. And so what we're going to do is this. We're going to evaluate this matrix, and you're going to have to realize that you're going to have x's and y's in these products that we're doing here. But what that'll do is allow us to solve for y, get y by itself, and in terms of x to boot. And also, that's the nice thing because we wanted to find the equation of this line to begin with. So here's what we're going to do. Find the equation of the line passing through these 2 points right here. I'll tell you what, I'll show you the quick and easy way to do this is just remember we're dealing with this special matrix here where we have ones down in the last column, and we're going to drop in our ordered pairs here. So we say our arbitrary point, any point on this line, here's another point on this line, here's another point on this line, and if they're all 3 on the same line, then this determinant has to be equal to 0. So let me space this out a little bit here. Actually, I'm going to write has to be equal to 0 because what I'm going to do is I'm going to extend my matrix here as I would if I'm finding the determinant of a 3 by 3. And we'll go ahead and say it's the sum of our down diagonals, the products of our down diagonals, minus the sum of the products of our up diagonals. So down diagonal here, we'd say x times 4 times 1, that would be a 4x. Y times 1 times negative 1, so we say plus a negative y here, plus, now 1 times 2 times 3 is a 6. And then over here we would get, now our up diagonals here, negative 1 times 4 times 1 is negative 4, plus 3 times 1 times x is 3x, plus now 1 times 2 times y is, of course, 2y. So we're saying all of this is still equal to 0. Now what I'm going to do is I'm going to change this to a sum, and I'm going to add the opposite in here. So this would become a positive. See, this here would become a negative. This here would also become a negative. So let's combine like terms. Looks like we get a 4x and a negative 3x. That, of course, would be an x. A negative y and a negative 2y is a negative 3y. And then our positive 6 and our positive 4 is a 10, and we get 0. So now, really, all I want to do is get y by itself here. We'll put it in slope-intercept form. So that means that I'm going to subtract x and subtract 10 from both sides. Subtract x, subtract 10. If you want to list our work here, we can say that those are heading out. So we get negative 3y would be equal to negative x minus 10. And so what I'm going to do here is, I think I can scroll down here. Ooh, cool. A little more room. We're going to divide everything here by negative 3 as we would. And the nice thing about a monomial divisor, a one-term divisor, is that everything in this numerator here we can divide by a negative 3. So I get a negative 1 divided by a negative 3, which is, of course, a positive 1/3. We'll put our x on the side. And then a negative 10 divided by negative 3 is a positive 10/3. So this would be the equation of the line, definitely, that passes through these 2 points here. And a good exercise would be, maybe pull up Desmos and graph this and go also type in these ordered pairs and prove to yourself that these actually go through those. So that's how you can find the equation of a line passing through 2 points using a determinant every time. Cheers.